Section: Introduction. In this section, we discuss how information retrieval (IR) has evolved over the past 20 years, shifting from sparse techniques like BM25 to neural language models as the foundation. These neural models typically produce a single embedding that represents the entire input, known as dense retrieval. They can adapt to new datasets and tackle more complex retrieval challenges. Recently, we have seen the emergence of instruction following retrieval benchmarks, where models must interpret various relevance definitions for different queries. For instance, the Quest dataset combines concepts using logical operators to assess the difficulty of retrieving complex queries, while the Bright dataset examines the challenges of varying relevance definitions that require reasoning. Although current models struggle with these benchmarks, they are designed to push the limits of dense retrieval capabilities. Instead of merely creating benchmarks to evaluate embedding models, we aim to understand their fundamental limitations. Since these models use vector representations in geometric space, we can leverage established mathematical research to analyze them. Our work connects theoretical results in geometric algebra with advancements in neural information retrieval. We utilize communication complexity theory to establish a lower limit on the embedding dimension necessary to represent combinations of relevant documents and queries. Specifically, we demonstrate that for any given embedding dimension, there are certain combinations of documents that cannot be retrieved, regardless of the query, indicating a theoretical limit for embedding models. To validate this limit across different retrieval models and datasets, we optimize the vectors directly with test data, allowing us to empirically show how embedding dimensions affect retrieval tasks. We discover a critical threshold for each embedding dimension where the number of documents exceeds the capacity of the embedding dimension to encode all combinations. We compile these critical points for various dimensions and find that this relationship can be modeled with a polynomial function. Additionally, we create a simple yet realistic dataset based on these theoretical constraints, called limit. Despite its simplicity, we find that even state-of-the-art embedding models struggle with it, particularly those with smaller embedding dimensions. Our contributions include 1. A theoretical framework outlining the fundamental limitations of embedding models. 2. An empirical analysis confirming that these limitations apply to any dataset through free embedding optimization. And 3. The limit dataset, which challenges even the best models. These findings suggest that while neural embedding models have achieved significant success, academic benchmarks often test only a limited range of queries, masking these limitations. As tasks demand models to return increasingly complex combinations of relevant documents, we will encounter limits that they cannot overcome. Therefore, we encourage the community to recognize these limitations when designing evaluations and to consider alternative retrieval methods, such as cross-encoders or multi-vector models, to effectively handle a broader range of instruction-based queries. In terms of related work, we note the significant advancements in embedding models, which have progressed from basic web search to sophisticated instruction following and multimodal representations. These developments have been driven by improvements in language models, including pre-trained and multimodal models. While our focus is on textual representations for clarity, our findings are applicable to all types of single-vector embeddings across various datasets. As the complexity of representations increases, we anticipate that these theoretical limitations will become more pronounced. Section Summary. In this section, we discuss the evolution of information retrieval from sparse techniques to neural language models, highlighting the limitations of dense retrieval models in representing complex queries and relevance definitions. We establish a theoretical framework that reveals fundamental constraints on embedding dimensions, demonstrating that as the complexity of tasks increases, these models will inevitably reach a point where they cannot adequately represent all necessary combinations of relevant documents. Section: Empirical tasks pushing the limits of dense retrieval. In this section, we explore the challenges of dense retrieval models that have expanded beyond their original applications to cover a wide range of areas. We note significant efforts to represent various domains, follow diverse instructions, and reason over queries. This shift has moved the focus of embedding models from simple keyword matching to capturing the full semantic meaning of language. Consequently, it is now more common to link previously unrelated documents in the top relevant results, which increases the combinations that models must represent. This has sparked our interest in understanding the limits of what embeddings can convey, as current expectations demand they handle every task. Previous studies have empirically examined the limitations of models, revealing that smaller dimension embeddings tend to have more false positives, especially with larger datasets. They have also highlighted the constraints of models in cross-lingual contexts and how embedding dimensions relate to the bias-variance trade-off. In contrast, our work establishes a theoretical link between the embedding dimension and the sign rank of the query relevance matrix, while also identifying empirical limitations. We delve into the theoretical limits of vectors in geometric space, noting that the study of nearest neighbors in semantic space has a rich mathematical history. For instance, the Voronoi diagram, which dates back to 1644 and was formalized in 1908, serves as a foundational concept. The order K Voronoi diagram, which shows the closest K points, is particularly relevant to information retrieval. However, establishing tight bounds on the number of regions in this context has proven challenging and offers limited practical insights for information retrieval. We approach this issue differently by demonstrating that the constraints from the top K retrieval problem can be formalized to indicate a lower bound on the dimensionality required for effective representation. We find that this necessary dimensionality can exceed that of typical embedding models used in practical information retrieval scenarios. Our method draws on previous work in communication complexity theory to establish bounds using the sign rank of a matrix. Given the complexity of calculating the sign rank, we utilize established results that have already determined the sign rank of known matrices. Additionally, we provide a proof of a method to establish a lower bound on the sign rank through what we refer to as free embeddings. In the next part, we prove how known results from communication complexity theory apply to vector embeddings. We consider a set of queries and documents represented by a relevance matrix, where a value of 1 indicates relevance. Vector embedding models map each query and document to vectors, and relevance is assessed through their dot product. Our goal is to find the smallest embedding dimension that can accurately reflect the relevance specified in the matrix. We define this in terms of the rank of the score matrix, aiming to determine the minimum rank necessary for the model to prioritize relevant documents over irrelevant ones. We also introduce a condition for separating scores of relevant documents from irrelevant ones by a threshold, which we formalize in our definitions. Section Summary. In this section, we explore the limitations of dense retrieval models by establishing a theoretical connection between the embedding dimension and the sign rank of the query relevance matrix, demonstrating that the required dimensionality can exceed that of practical embedding models. We also formalize the relationship between queries and documents through a relevance matrix, aiming to determine the minimum rank necessary for effective document retrieval based on relevance. Section: Theoretical Bounds. In this section, we discuss theoretical bounds related to binary matrices, where row-wise ordering and row-wise thresholding represent similar concepts of capacity. We propose that for a binary matrix A, the row-wise order rank is equal to the row-wise threshold rank. To prove this, we first show that if a matrix B meets the row-wise thresholdable rank condition, then it also satisfies the row-wise order preserving condition. This is because if one element in A is greater than another, it implies a similar relationship in B. Conversely, if B meets the row-wise order preserving condition, we can define sets of elements based on whether they correspond to ones or zeros in A. We can then find a threshold that separates these sets, confirming that B is also row-wise thresholdable to A. We also introduce the concept of sign rank, which is crucial for our main bounds. The sign rank of a matrix M is defined based on the signs of its entries. We denote a vector of ones and a matrix of ones for our calculations. Next, we establish that for a binary matrix A, the rank of A is less than or equal to the rank of a modified matrix derived from A. We prove this through a series of inequalities, showing how the ranks relate to each other based on the properties of the matrices involved. The implications of our findings are significant for vector embedding models. They provide both lower and upper bounds on the dimensions needed to accurately represent a set of retrieval objectives. Specifically, for a binary relevance matrix A, we need at least one less than the rank of the modified matrix to capture the relationships in A exactly, and we can do so in at most the rank of the modified matrix dimensions. Practically, this means that for any fixed dimension, there are binary relevance matrices that cannot be represented in that dimension, especially if they have a high sign rank. Thus, retrieval tasks with higher sign ranks are inherently more challenging and require higher dimensions for accurate representation. If we can embed a matrix A in a row-wise order-preserving way within a certain number of dimensions, it gives us a bound on the sign rank of the modified matrix. This suggests a useful method for estimating the upper bound of sign rank through optimization techniques. Section Summary. In this section, we establish that for binary matrices, row-wise ordering and row-wise thresholding are equivalent in terms of representational capacity, leading to bounds on the dimensions required for vector embeddings to accurately capture retrieval objectives. Specifically, we show that the dimensions needed range from one less than the rank of a transformed matrix to the rank itself, indicating that higher sign rank matrices necessitate greater embedding dimensions for accurate representation. Section: Empirical Connection, Best Case Optimization. In this section, we have established a theoretical limit for embedding models based on the sign rank of the Kirel matrix and the embedding dimension. Now, we aim to demonstrate this empirically. To achieve the best possible optimization, we design experiments where the vectors can be directly optimized using gradient descent, which we refer to as free embedding optimization. This approach allows us to see if any embedding model can solve the problem. If our free embedding optimization fails, then real retrieval models will also struggle. We optimize the embeddings directly against the target Kirel matrix, focusing on achieving the highest performance possible, even though this won't generalize to new datasets. For our experimental setup, we create a random document matrix and a random query matrix with top K sets, both consisting of unit vectors. We optimize these using the Atom optimizer, processing all correct triples in each gradient update with the info_nce loss function, treating all other documents as negatives. We normalize the vectors after each update and stop early if there's no improvement in loss for 1000 iterations. We gradually increase the number of documents until we can no longer achieve perfect accuracy, which we call the critical endpoint. We keep the sizes of n, k, and d relatively small to avoid combinatorial explosion, as larger values lead to an overwhelming number of combinations. We use k equal to 2 and increase n incrementally for each d value until we hit the limit. We then fit a polynomial regression line to model and extrapolate our results. Our results indicate that the curve fits a third-degree polynomial, allowing us to extrapolate critical n values for different embedding sizes. We find that even in the best-case scenario, real embedding models cannot directly optimize to match the test Kirel matrix due to constraints like modeling natural language. This suggests that for large-scale web search, even the largest embedding dimensions with ideal optimization are insufficient to cover all combinations. Next, we connect our findings to real-world datasets. While our free embedding experiments support our theoretical results, we need to understand their implications for actual embedding models. Existing retrieval datasets often use a static evaluation set with a limited number of queries, which means they only sample a tiny fraction of potential queries. For instance, the Quest dataset has 325,000 documents and queries with 20 relevant documents each, but the number of unique top 20 document sets is astronomically large. Thus, the 3,000 queries in Quest represent only a minuscule part of the possible Kirel combinations. Although it's impractical to cover all combinations in large-scale datasets, evaluation datasets should ideally test a wide range of combinations, reflecting user queries. However, many developers opt for fewer queries due to cost and computational constraints. For example, Quest's query about novels combines two categories, and new queries could be generated by combining other categories. With the rise of search agents, we see more specific queries, like those in Browse Comp, which include multiple conditions. This indicates that the choice to limit combinations in existing datasets is more about practicality than feasibility. In contrast, we aim to create a dataset that evaluates all combinations of top case sets for a small number of documents. Instead of using complex query operators, we focus on simple queries and documents to emphasize the challenge of representing all top case sets. Section Summary. In this section, we demonstrate the empirical connection between our theoretical findings and real-world embedding models by conducting free embedding optimization experiments, which reveal that even under ideal conditions, the largest embedding dimensions struggle to model all possible query document combinations. We also highlight the limitations of existing retrieval datasets, which cover only a minuscule fraction of potential queries, and propose a new dataset designed to evaluate all combinations of top case sets for a small number of documents. Section: Models. In this section, we evaluate several advanced embedding models, including Grit-LM, Qwen3 embeddings, PromptReaver, Gemini embeddings, Snowflake's Arctic Embed Large version 2.0, and E5 Mistral Instruct. These models vary in their embedding dimensions, which range from 1024 to 4096, and in their training methods, such as instruction-based or hard-negative optimized approaches. We also assess three non-single vector models, BM25, GTE Modern Call BERT, and a token-wise TF-IDF, to highlight differences. We present results for both the full embedding dimensions and truncated dimensions, commonly used in Matryoshka learning, MRL. For models not trained with MRL, we expect lower scores, so we mark those trained with MRL with stars in our plots. Since no large language models have an embedding dimension smaller than 384, we include MRL for all models down to a dimension of 32 to illustrate the effects of embedding size. Our results reveal that models struggle significantly, even with a straightforward task. In the full setting, models fail to achieve even 20% recall at 100, and in the smaller 46 document version, they cannot reach recall at 20. We find that performance is heavily influenced by embedding dimensionality, with larger dimensions yielding better results. Notably, models trained with a wider variety of instructions, like PromptReaver, perform better, likely because they can utilize more of their embedding dimensions compared to those trained with MRL on a narrower range of tasks. We also observe that alternative architectures perform better than single vector models, although they still do not solve the task completely, while BM25 approaches perfect scores. These alternative architectures, which include sparse and multi-vector models, present different trade-offs, as discussed in the alternatives section. We then consider whether a domain shift might be affecting performance. Although our queries resemble standard web search queries, we hypothesize that training on a similar set of examples could enhance performance. Conversely, if the task is inherently difficult, training on the training set would yield little improvement, while training on the test set might lead to overfitting. To investigate this, we take a pre-existing embedding model and fine-tune it on either the training set or the official test set of limit. We use Lighten-I, ModernBERT embed large and adjust the hidden layer size during training without MRL. Our findings show that the model trained on the training set does not solve the problem, with only a slight improvement in recall at 10. This suggests that the poor performance is not due to a domain shift. When we train the model on the test set, it learns the task and overfits to the test queries. This aligns with our earlier results, indicating that overfitting is possible even with a small version of the dataset. However, it is important to note that the actual embedding model with 64 dimensions still struggles to solve the task, highlighting that real-world models are significantly more limited than free embeddings. Lastly, we discuss the impact of QREL patterns on the difficulty of limit. The key challenge is that limit tests models on more document combinations than typically encountered. To explore this, we examine different QREL patterns. 1. random sampling from all combinations. 2. A cycle-based setup where each query relates to documents from previous queries. 3. A disjoint pattern with new documents for each query. And 4. A dense pattern that maximizes connections among documents. For all configurations, we maintain the same setup as the main limit, which includes 50,000 documents and 1,000 queries. Section Summary. In this section, we evaluate various state-of-the-art embedding models and their performance on a challenging task, revealing that models struggle significantly, particularly with lower embedding dimensions. We also investigate the impact of training on different datasets, finding that poor performance is not due to domain shift but rather inherent limitations of the models, especially when tested on complex combinations of documents. Section Results. In this section, we observe that all patterns, except for dense, perform similarly. However, when we switch to dense, we see a significant drop in scores for all models. For instance, Grit-LM experiences a decrease of 50 in absolute recall at 100, while E5 Mistral shows an almost tenfold reduction, going from 40.4 to 4.8 in recall at 100. When we compare our results on the limit dataset to BEIR, which is often cited as a benchmark that embedding models may have overfitted to, we find that there is generally no correlation in performance. Smaller models, like Arctic Embed, tend to perform worse on both datasets, likely due to their embedding dimensions and the knowledge from pre-trained models. Our earlier findings indicate that embedding models cannot capture all combinations of documents in their top sets, limiting their ability to tackle certain retrieval tasks. Although larger embedding models have mitigated some issues for smaller datasets, the dimensionality would need to increase to impractical levels for more complex datasets. This presents a trade-off. While embeddings can represent many combinations, they cannot represent all. They may be useful for initial results, but we will need more expressive retrieval architectures. We also discuss cross-encoders, which, while not ideal for large-scale first-stage retrieval, are often used to enhance initial results. We tested a long context reranker, GEMINI 2.5 Pro, on a smaller setting and found that it successfully handled all 1,000 queries in one pass, achieving 100% success. This contrasts sharply with the best embedding models, which had a recall of less than 60% at rank 2. Thus, limit is manageable for state-of-the-art rerankers, as they do not face the same dimensionality constraints. However, they are more computationally intensive than embedding models, making them unsuitable for first-stage retrieval with large document sets. We also explored multi-vector models, which utilize multiple vectors per sequence along with the maxsim operator. These models performed significantly better on the limit dataset compared to single-vector models, even with a smaller backbone like modern BERT. However, their effectiveness in instruction following or reasoning tasks remains uncertain. Lastly, we consider sparse models, both lexical and neural, which can be viewed as single-vector models with high dimensionality. This high dimensionality allows BM25 to avoid some issues faced by neural embedding models. However, it is less clear how to apply sparse models to tasks that require instruction following or reasoning, where there may not be any lexical overlap. We plan to explore this area in future work.